Hey everybody, how are we doing? It is Thursday, Haslam Friday. What a better day than Haslam Friday, because no classes on Friday. Well, at least in Haslam. Anyways, I hope everyone's doing well. I might there was a few questions. I got a question via email if I could talk about number 5 from 320 from last night. So let me go over to number 5 from 320. So I'm going to pull up the 320 assignment and go over to number 5 from last night's assignment. I think this was some stuff with the all correlations. And so the solutions are also posted. And so we should have, let me make sure. There we go. Okay, let's hop over here. And if you hop in here, feel free to ask some questions. We'll see if some people join up. Probably a light day today because a lot of assignments were due. 201 had tests. So I might do some fun stuff here towards the end. If I'm here by myself, then we're gonna do some partition models and stuff like that. But if you join in, then feel free to ask questions. We're gonna I love coding, as everyone knows. Let's hop over to coding. Here, class is not over. That's my class over screen. Class was over. But we've got here number 5. And let's go down. Number 5. Run the correlation demo right here. So this is a good review of correlation, and we've got a whole bunch of questions about doing correlation. So the first one is to generate a scatter plot that has a correlation of about this, negative 0.8, plus or minus that amount. So we need to have library reg class running right here. And now we need to run core demo. And we're going to make core demo a lot bigger. Now, a few people emailed me, or I think it was on Discord, we saw a few comments of maybe core demo is a little crowded. If you go to view, zoom out, you can zoom out a little bit here and get it to kind of be on the screen a little bit better. And now we want to make a correlation of negative 0.8. So I kind of set myself up for failure to start. Looks like we get, there we go. There's negative 0.8. So we can make a correlation of negative 0.8. We just need to keep going closer here. Try to remember if I wanted it to be, oh, come on, let's go a little more. There we go, there we go. And here, too far out. If you go towards the center, it gets stronger. If you go toward, there we go. There is a correlation of negative 0.8, and you can see it goes downwards. And it's just a good program to kind of go and do the correlation. Have this correlation be displayed. I think this one's good right here. This is 5A. And then 5B is generate a scatter plot with stream points with an extreme outlier. Without the red dot, the stream should have a correlation of 0.7, give or take, plus or minus this. And then the stream should have this, should have 0. So we should have a correlation. We'll start a new one right here. So we're going to make a correlation of 0.7. Now I start with usually a strong correlation, then I make it weaker so I can kind of go out and make more of a circle. And that's close enough, but we're going for perfection right here. I'm making it too strong there. Go weaker, there we go. Stronger, there we go, great. So that's a correlation of 0.7. If you go right about there, you see, since if it's high correlation, I'm going to bring it lower. So if it were to be too low, I'm going to raise it up. So we can get an idea that it's going to be right about there. And now it's going to be a little lower. And there we go. So that's an extreme outlier right there, making a strong correlation weak. So we're trying to see, when does a strong correlation become weak? When does a weak correlation become strong? And outliers can do anything. Generate a scatter plot which has a stream of points with an extreme outlier. Without the outlier, the stream should have a correlation of 0.2. Oh, wait. Oh, 0 plus or minus 0.2. I was like, I don't remember that question. So it should have 0, and with the outlier, it should have a correlation near 1, at least that amount. So let's go ahead and redo our plot right here. And the easiest way to make a correlation of 0 is to make a box. Perfect box today. I mean, it's a little off, but at least it made a 0. And then if you go way over here, you can get a correlation of basically 1. Now, if you want to make it really close to the answers, you go really close in here. Oh, I think I have an extra point that I can't see. Let me do it. Or else it's so hard to, I don't usually do it this. Wow. On fire today. No one's here to see. No one's here to see me getting all these up. There we go. That is the correlation of 0, and that is, if you look at it, it makes a line now, and you can see how there would be a linear relationship. Trying to put it along the line right here. Of course, this follows the linear relationship. There's a little bit of a bend through here. It's enough that the decimals round up. I was trying to make the line, but previously I had it warning, sure. And I think, is that the last one? That's all the question fives right there. Was a question, can you do question 5? One of the things I want to take a look at is I want to maybe look at some partition models in R, and maybe talk about some of the advanced partitioning stuff, and maybe give 474 a little peek into the future of what we'll be doing with partition models. So let me get some stuff up here in the background. So partition models. So there's so much you can do with partition models. Let's go over here because I wanted to use a forest. Let's do a forest and the rattle package. There's a package called rattle, which does fancy R plots. I should have it on here. There we go. And I need library caret. And if you are here, feel free to ask questions. If you jump into the chat, I think we're streaming. So let's go here. You know what I might do? I might bring up something real quick here. Let's bring up some notes and show the notes. So we're going to bring up some notes right here. This is, if you're in 474, this notes section I'm about to open is the most amazing, most helpful thing. So it is the data mining notes, and it has everything. It has all the things you need to know. And so let's go and grab it really quick right here. And that's not it. Do we have it posted right now? Oh, we might not have it posted, so I'll need to grab it. If you are here, feel free to say hi and jump in and ask questions. I thought I saw something up here. I did. Dan, could you possibly go over quantitative variables as response variables in decision trees? Yeah, let's do that. Here, we'll do it in jump. That's going to be easier to understand on the 201 level. I was going to do some advanced. You are welcome, Dan. Let's do it. Or I didn't say thank you. I'm glad you're here, Dan. I really appreciate it. Here, I'm going to put the class over. Class is not over. This is the screen I put up when we do this right here. And this is the data set we were using yesterday right here. So when you have a quantitative variable, I'm going to go ahead and go to rows, clear row spaces. So when you have a quantitative variable, you're actually going to be predicting the mean for each leaf. Terry had to change the format of the, yeah, I saw that. I changed it too. You can do a quantitative variable. And so I changed it, and I probably should send an announcement about that. I just saw he sent an email earlier today, and I changed it because now it's doing a categorical, and you can do quantitative. So we could predict somebody's exam 1 score. So I can predict someone's exam 1 score, and the trick I use, well, one, none of these variables are indicators, or not indicators, identifiers. So we don't want to include identifiers, but luckily none of them are identifiers. So I'm going to put all the variables there. None of them are identifiers. I know that. Nope, none of them are identifiers. I'm pretty certain. Or act like identifiers. You don't want those in there. Now we're going to put exam 1 score here. So that's a quantitative Y. And we're going to go ahead and click OK. Now the way this is going to split up the data is it's going to split it up by the mean. So when we do a split right here, it's going to try to separate people who have low exam scores into one group and people who have high exam scores into another group. And what it's going to do is it's going to look through every one of these variables, and it's going to say, okay, what if I do it on tailgating? What if I do it on slow annoy? What if I do it on speed annoy? It's going to look through every one of these variables right here to find the best possible variable to split on. And the best possible variable to split on is, I had a drumroll button, but I deleted it. I do have a wow button though. There we go. It's scholarship amount. So the best possible variable to explain someone's exam 1 score was scholarship amount. And then it finds a place to split on it. It says, okay, people who have a greater than or equal to $1,000 in scholarship amount, their average exam score was 82.17. It also gives the standard deviation. So think about it like a normal distribution, that the scores were normally distributed. We shouldn't say they're normal unless we see it. But if we're using mean standard deviation, we're probably talking about the normal. But this is the mean and the standard deviation for this group of students, which encompasses 556 students. This is the mean and the standard deviation for this group of students, which is 174. And you can kind of see where it's splitted. If you look up here, you can see the split right here. Here is your 174 students right here. That's 174 students. Did it actually split? Kind of. It's interesting how it's interesting how it's split. There was a whole bunch at the first of it, but those are the 174 students, and these are the 556 students. So the 556 students are in this group down here, and then the 174 students are here. And it's weird to me how they're kind of clumped together. The data might be organized in a certain way, but you'd expect it to be more random, not getting these clumps. But data is the way data is. And then we're going to split again. So we got 4 splits total, and we'll make it full screen here. And we're only explaining 5% of the variation. And I don't think this is really a good tree. The easiest tree to do here, I'll do the easiest tree, is to go here and do a tree that predicts something like somebody's weight. So if we predict somebody's weight right here, this is going to be an easier tree to do. We're just going to go split, and automatically 35% of the variation in someone's weight is explained by the variation in their height. Now, you could say the variable's in the tree, but right now there's only one variable in the tree. And we see here that people who have a height greater than or equal to 70 inches had a mean weight of 180.4 with a standard deviation of 30. People who had a height less than 70, which there was 461 of these individuals, had a mean weight of 139.4 with a standard deviation of 24.8. So when you think about it, you've kind of got the lighter people here and the heavier people, and we've already explained 35% of the variation in people's weights. Now, Dan, let me ask you this. If we explain 100% of the variation in people's weights, then what would that mean when we make predictions? Or if we use this model? If we explain 100% of the variation, all of our predictions would be what? If we explain 100% of the variation, if we get an R squared of 100, every prediction would be what? If R squared were to eventually reach 100, all of our predictions would be what? Because this is what R squared is. As R squared goes up, it's the predictive power of the model. And if you had an R squared of 100, all your predictions would be what? They would be perfect. They'd be perfect. They'd be exact predictions. As in, you would say, Brian, I predict you weigh 182 pounds. The predictive power goes up as R squared goes up, because check this out. Boom. Now we're using another X variable right here. And good answers, Dan. So we're using another X variable right here. And there we go. That's Adrian Croissant. We're using another X variable right here, and we can see, and it's using the same one. It can split on the same variable. Trees can do that. It's just that height is a really good explanatory variable. Now we have 44% of the variation, and eventually we'll probably get a new variable here. Oh man, height is just so good. And there we go. There's gender. And you know what's interesting? These are people right here who are between 5'10", and also they're between 5'10" and 6.6 feet and a half inch. So these people are pretty tall for females and kind of tall for males, like above average males and pretty tall females. So you look here, the males who are a little bit above average weigh on average 175, and the females who are quite a bit above average weigh 147, and we're up to 47% of the variation. Now I'm interested over here because this is where I'm at. Actually, this is where I'm at right here. Let's see how good of a prediction it makes for me. Okay, so then a lot of people want to know, and I have to vanish here because I'm blocking the screen. A lot of people want to know how you use this tree. And the way you use the tree is you just ask yourself the questions. Is my height greater than 70 inches? Yes, greater than or equal to. Is my height greater than or equal to 6'1.5" inch? Yes. Is my height greater than or equal to 6'3"? Exactly 6'3". How annoying do I find slow drivers? I mean, really annoying. And then the model would predict I am 197.5 inches. So you can actually do the residual here for Brian. Since I weigh 182, my residual would be, think actual minus predicted. So I'm below the prediction. So I'd be negative 15.5. Now we never talked about residuals in this chapter, but you can do things like residuals. You can figure out how far off this tree is from each individual. I think you can go to save residuals here. It is in the notes. We've never done it. It's just because you can save residuals. So you can save the residuals. And it just would tell you how bad each of these predictions are when you make predictions. So, and this goes a little bit more advanced, Dan, to say this, like, because we talk about this in 474 a little bit, because we do it with coding. The point of this tree is to make predictions. And when you think about it, you would predict Brian is 197.5 inches, but if you talk to another person, you'd predict any of these other weights down here. Hey, Brian, what's up? Yusuf, so good to see you. This was on your recommendeds. Well, Yusuf, you're a mod right now. I'm adding you as a mod, Yusuf. So good to see you, Yusuf. Hope your semester's going. Are you a junior or senior now, Yusuf? You don't have to say in the chat. Don't worry about it. But I'm just thinking about it. I'm like, Yusuf took my class. Man, help here on the screen again. You're a senior. Congratulations, Yusuf. Hopefully you remember decision trees here. We got AIC Akaike's information criteria right here. We don't need to know that in 201. We got log worth and Gini index. I thought Gini index was on here. Oh, that Gini index is on the other tree. Gini index is the impurity of the leaves. So it's an impurity measure to tell you how impure the leaves are. And you want pure leaves. So you want the Gini index to decrease. And so knowing the difference between these trees, and there's the Gini index and the log worth. So, and you can tell this one has a lower Gini index because it's more pure. So to lightly go into the advanced stuff right here, log worth, I haven't interpreted log worth. Oh, it tells you? Measure significant calculated so a p-value of 0.01 is a log worth of 2. Oh. I've never done that. Wait, what is it calculating the significance of if we... Oh, is it telling you the significance of each split? What? Why didn't I hover over and read this? I'm learning something right here. Log worth measures significance, so a p-value of 0.01 is... Okay. So this tells you how significant each split is, so you can look to see if each split is statistically significant. So this is a super significant split right here. And this split right here is also super significant. And this split right here is very, very significant. It's basically how many zeros are on it because it's a log. Why don't they just call it log p-value? It's log worth. And just hovering over it, Gini index is impurity, is the likelihood ratio of the chi-squared statistic. Oh, it's impurity. So that's what I call it. It's the amount of impurity in the leaves. And if we see here lower impurity, but it's also based on the sample size. So yeah, we see a lower Gini index here and a higher Gini index here. So yeah, you can tell the 50-50 one should have the higher. So the closer it is to a 50-50 and the more things that are in it, the higher the impurity. So you can see right here, we have lower impurity. But really interesting stuff. I always like looking into like what's going on here. Are we getting more significant splits? Now that I know how to look at the p-value, that's statistically significant. That's 0.001. We're starting to get into some really, yeah, statistically significant. It's getting kind of iffy now. How could I look at? Oh, no problem. Good to see you again. Definitely, anytime, man. Good seeing you, Youssef. And if you need any letters of recommendation, let me know. Great job. I've got to write some this weekend. And so good to have you swing by. So good seeing you, Youssef. And if you look, this looks just like a mosaic plot. Because that's what we're making right here. Is we're making a mosaic plot. We're splitting it into groups. And now we go here and we go to split history anytime. Split history. Boom. We probably should have stopped about here. I don't know. We're really not getting that much of a return. Our R squared jumps up and levels off. So even though those are statistically significant, and there's other ways to look at this with complexity parameter, but I'd probably go back to about there. So the split history shows you the increase in R squared. The goal of this is to get a high R squared, explain the variation in the Y variable. And if we had something that explained all the variation, which I can show an example of that. So let's show an example where we explain all the variation. So let's go here to pass, fail. And I wish this was how class, we did an example yesterday and it worked all right, but I might try to collect more data. So we're going to put all this right here. The best way to know when to stop splitting is the R squared starts. Exactly. That's in this class. In this class, I could pull up some other notes and show you the real way we do it. But in this class, we're like, okay, where does it level off? Which is kind of the way we do it. But there's something called the complexity parameter where we're looking at the increase in the change in R squared. And we actually calculate, when it's not getting a good return. So the complexity parameter is basically the return in the remaining variation there is to explain. So think about this. Imagine there's a pizza and the first person comes in and eats how much of the pizza? So there's a pizza right here and the first person comes in and eats almost half the pizza. Does that make sense? The first person came in and ate almost half the pizza. At this point, if the next person came in and ate almost half, well then that'd be amazing because we'd be up to like 90% of the pizza eaten. But we would then have smaller increases generally because there's less of the pizza to eat. You can only eat 100% of the pizza. And then when we look at this here, we expect smaller increases, but they're kind of worth more. Like if you go from 90% to 100%, that's amazing. If you go from 0 to 10%, it's something. So what we do with the complexity parameters, we look at the remaining variation left to explain, and then we use different cutoffs. And generally there's a suggested complexity parameter, kind of like guidelines we go by, but you can once again kind of pick and choose from where to go. And you look at the tree, and then there's really crazy stuff. And JOM can do some, I'll show you something really crazy JOM can do here in a second. But you are correct, in the 201 standard way we do it, which is an all right practice, is to kind of look at it and say, where do we get less of a return? And I think someone said yesterday during class, they said it's kind of the second derivative in calculus. If you think about when does it stop increasing so much, like we have increasing, and probably in here somewhere is where we're getting this leveling off. It's increasing would be first derivative, and the rate of increase is going to be second derivative. So I guess, is that where the second derivative is probably changing here, because it's still increasing, but it's increasing at a decreasing rate. So I think that's it. It might be. So maybe 2, 3, 4, somewhere there. So we probably want a tree that looks like this. This is 3 splits, or this. Those are your trees to consider. And you could, in statistics, you can make all 3 of them. I'll keep in mind when the visualizations come up. Yeah, and I think in the assignment, I might have the assignment up because I was looking at it earlier. In the assignment, yeah, here it is. In the assignment, it specifically says, I think it tells you how many splits to do. It says, I was reading it, take 3 splits. So here's the suggestion. The easiest trees to look at are going to be symmetric trees. And not that you shouldn't not look at symmetric trees, but I've suggested to students, because one, we're just trying to make sure you understand how to read this. We're not trying to solve the world's problems with this. But if you notice, when I make my tree, it'll choose the direction the tree goes. But I could choose a variable right here to split on, not choose the variable, well, you can if you do this, but you can choose to split here and get a symmetric tree, which is a little easier to kind of see the pathways and see the bottom terminal leaves. So it's all right to do this, because once again, we're just looking for understanding. In practice, you won't direct the tree what to do, but it's more, can you interpret a tree? Do you understand what the output means? And so if this is a little easier to look at, especially for looking at just some starter trees, I've often suggested it. And if you notice, take a look down here at my split history. I've now got 2 separate paths, and you can actually see that the path I chose was not the optimum path. You can see the R² for my current path, and then the other one it had me doing was a higher R². So it's showing the 2 different R² because I have 2 trees right now with 3 splits. Here's my tree, and then here's the suggested tree with 3 splits, which has the higher R². Oh, we actually converged towards something. Oh, I think because I might have went forward then backwards. But, oh, I hit split. I didn't hit prune. Oh, that's what I should have done. So it actually converged back. That's pretty interesting. It's kind of knowing what the visualization is showing you is key, that this is what the R² was for each amount of splits. So now that I have 4 splits, or 3 splits, excuse me, I'm right here. And then when I go to 4 splits, I go to right here. So even when I directed it to do something, it achieved this split on its own. And then here's the extra split we got. What you can do that's really crazy is you can do the following. And we do this in the upper level classes. You can go here to a bootstrapped forest. A bootstrapped forest, or a boosted tree. Well, boosted trees are completely different. I've never done a cane. Well, I know a cane. Yeah, I know. I thought it was a cane nearest neighbor forest. We're teaching cane nearest neighbors like right now. I taught it earlier today. I thought it was some sort of forest though. So the bootstrapped forest is going to make a ton of random trees. So I'm going to make 1,000 trees, and then number of terms in each split. That's going to be how many X's are included. The sample rate is how much it resamples my data, minimal splits. There we go. And let's run this. And now it's making 1,000 different trees. So it's literally making random samples of my data and making 1,000 different trees. And this is kind of the more advanced things we do. So instead of just making 1 tree, we now have 1,000 trees working together. And this is how well I'm able to predict if someone's male or female. And my R² is at 75% now, or 76 when you round up. Or the generalized is 87. But so I'm doing really well right here. 87% of the variation in whether someone is male or female is explained by the variables or my forest. So you could use this here to make predictions, and you could see how well it does. And so we'll just look at this one thing. Feel free to ask questions. I know I'm just kind of talking about hopefully nothing that's too confusing to anybody. But here is how the model does. Let's take a look. We have gender being explained by the predicted gender of the tree. And there's the probabilities. So that is how the model is doing. Wow, it's an R-squared at 93%. So you get all these cool graphics right here. And of course, the probability male, the probability female, same sort of thing right there. But it really explains it really well. And I'm looking at the probabilities right here. Maybe I'll switch it. Would it be logistic if I switch it? It's doing probabilities. Try to see right here, because these are the high probabilities. It does really well. There's some misclassification right in here. If you look at where the misclassifications are going to be, those are the misclassifications, because these blue dots are people who are male, but they had a low probability of being male. And then these dots up here were people who had a higher probability of being male, but they were female. These dots right in there, those are misclassified females. So pretty impressive that 93% of the variation is explained. And yeah, this is what I think is so cool, that you can do these things and do them so quickly. I just want to save the predicted. Yeah. And we can do this with R or something, but feel free to ask questions. I'm thinking, let's do another decision tree right here just to make sure we see it. Should we do a quantitative or a categorical? Let's see, a quantitative or a categorical. And feel free if anyone's watching to say, do this tree. Let's do a decision tree on, let's see here. I'm seeing if I see something that jumps out to me. So many crazy variables in this. Batman or Superman? Let's do it. Let's find out why people like Batman or Superman. So we're going to recolor the points right here, an important thing to usually do when you start this off. And we know a lot right now. We got the Gini index, which is a measure of impurity right there. We don't need to know that. 730 observations. R-squared is currently 0 because we haven't split the tree at all. And we have numbers split 0, and we have 730 observations. We split the tree. Oh, not as statistically significant. Found that out earlier. And then we have an R-squared of 2.3%, which makes sense. Since the R-squared is lower, we've explained less of the variation. And then this is how many zeros are on the p-value, as in 0.0000. And then it's a log value, so I'm not going to convert it. But we have here that people who are greater than or equal to 67 inches are more likely to like Superman. So taller people are more likely to like Superman. Next, we get someone's credit card limit. People who don't have credit cards, because this is a credit card limit less than 1, so people would not have a credit card, are more likely to like Superman. Oh, we got a big Superman group here. And hours you work a week. So if you work a bunch of hours, so if you're a taller person who doesn't have a credit card, but what we're seeing right here, I think we're finding, because this one was not that, I mean, statistically significant, but not that awesome. And so I'm really wondering if we're just looking into variables that we shouldn't be looking into, because we only have 5.7% of the variation explained, and none of these seem that related to liking Batman or Superman. So I really think we've went down a wrong rabbit trail with this one. We'll do an actual one that I know we can do. It's kind of a bummer, because if you're trying to find things that might be interesting, sometimes you just can't find them. One of the easiest ones to probably do, well, that one has so many variables. Change your sheets. Let's see. We did Broken a Bone. I've done Broken a Bone 1,000 times because it's an easy one to do. It's one that makes sense. The most likely thing about breaking a bone, oh wait, exercise 30 minutes. It's if you exercise? What? Maybe I've never used this data set for Broken a Bone. So the people who exercise more are more likely to break a bone. They're more active. That makes sense. And then how much you pay for a computer? Do I not have gender in here? I think I might have lost gender, because usually gender comes up. Oh, it's another data set maybe that doesn't have the same relationship. Wow. I am totally confused, because I thought it would come out completely different, and we're not getting that high of an R-squared again. I know I've done Broken a Bone before, but maybe it was through a different data set. So that one didn't turn out well either. It's all kind of luck, I'd say, if you get a good one. Let's try right here. Let's go with, we already did height, and that's just too easy. let's do you play video games? There's a quantitative one. So this is how much do you play video games? Someone plays video games all day, every day. And the number one thing is male or female for playing video games. And you see the males on average are playing 6.1 hours, where the females are playing 1.46. And then we have, what do you think of Gangnam Style? And I love it. I love it because I'm just such a huge nerd. And it's like people who are nerdy maybe would like Gangnam Style a little bit more. Gangnam Style is Psy, Open Gundam Style. And so people who really like Gangnam Style and are males are playing 18 plus hours of video games a week, or on average 18 hours. And then we get a split here on exam 1 score. That's so interesting. The people who had the exam 1 scores equal to, and it was statistically significant, greater than or equal to 100. So basically, these are people who aced the exam, are playing a bunch of video games. Now, these are small groups, and we have 20% of the variation explained, and we could do a split here. And this is if you exercise. So the people who exercise are more likely to play video games. I'll be. It's not statistically significant though, so I'm going to remove it. Prune below. So when we make our leaf report, which shows us inside the leaves, we can see how many individuals are in each leaf, and we can see the means for each leaf. So understanding what you get right here with the leaf report is very important. And I'll see, Dan, if you have any questions, let me know. I think I might do an advanced decision tree right here. So I'm going to go and grab the advanced nodes and show some stuff right there for 474. But feel free to ask questions. Hopefully that brings some more clarity to decision trees and kind of reading the output. And there's always so much more we can do with these things, which is what I love. We kind of introduce some topics in 201, and then there's super advanced, just so many things. So many things. That would be, okay, this is the one right here. Okay, so in the modules, yeah, here it is. Did I put this in their class already? Let's go to the R documentation. You're about to see a bunch of code, tons and tons of code right here. Here we are, tons of code. So let's take a look. Okay, we got knit R, which is knitting. And then we've got reg class, we got robust base, we got mass, we got caret, and we got plotrix. Cool. Okay. So let's go down to a forest. If I could spell forest. Random forest. So all this code right here is what we use to make a random forest, but the real thing we're looking at right here is going to be, that's a boosted model. We don't want boosted trees. Let's just go to the forest and let's uncomment out this code. So we'll go here. There we go. We now have our code back, and we actually need to talk about what this code does. I'll make this look a little bit easier by breaking it apart and making the code easier to read. So this should be helpful for some 320 and for some 474. So if you're in the chat, if you have any questions, feel free to ask. We're going to go through what this code has right here. Why are these commented out? There we go. I think I got everything uncommented. There we go. And so the main thing we're going to focus on right now is, one, the fit control, which is going to be super important in data mining, and two, the train function right here. So when we do the fit control, this is how we do the validation, which tells us if our model is accurate. So the validation is going to be an internal check of the model to tell us if we are actually making good predictions. It puts apart part of the data and checks to see if our model can actually predict. So it makes a model on a few of the chunks and then checks it on one chunk. So I go in more detail during class, but this is how we do it right here, just an internal check. But the main focus right now is going to be this mammoth of a function. Is this program free? I want to start learning it from One Story for that one story game we were talking about the other day. Oh, yeah, Nick, it's 100% free. Let me send you the playlist, Nick, on how to install it. I have a playlist for this. Good to see you here, Nick. And I'm just kind of rambling. I'm going to talk about this right here, but let me send you the playlist. We got 3 people watching. Yes, Nick, you're one of the 3 people watching. Getting started in R help. Okay, so wait. Is the getting started? Did I put those in there? Getting started in 201 help. Oh, I clicked the wrong playlist. Getting started in R. Here we go. Okay, so here is the playlist. I'm on YouTube watching YouTube now. There we go. And here is the playlist, Nick. This has how to install R and install RStudio. It's 100% free. And then I go through the color schemes. I go through some mathematics. They're all 1-minute tutorials. So you can learn some quick and basic stuff. Check it out and tell me what you think and ask questions and I'll let you know. Because then you'll build your way up to things like this right here. And so what is this? This is just right here a set seed for randomness. So this is going to control the randomness. I'm going to go over here to a new document so we can kind of see something. I'm working in an R script right now. It's just where we do programming. And if I run a code right here where I say sample the numbers 1 through 10, this will give me one number in 1 through 10. It's giving me a graphics error, but that's not really an error. It's giving me a number 1 through 10. Does this make sense with this code I'm running right now, does Nick? This gives me a random number 1 through 10. It says sample from the numbers 1 through 10 and give me one number. So that's what that code does. It says give me one random number 1 through 10. You could put in here 2, and now it says give me two numbers in 1 through 10. So there's two random numbers. You could do another argument, replace equals true, and now the two numbers I get could be repeating because I'm saying replace the numbers, and eventually, there we go. So when I do replace equals true, it can give me the same number multiple times. Like now I could ask for 100 numbers, and since it's replacing them, it gives me 100 numbers 1 through 10. Does this, hopefully, Nick, this makes sense right here. These are the numbers I'm sampling. This is how many I want. And then this is if it replaces them, like after it draws a number, if it then replaces it. So you might be wondering why I have this set seed here before it. The set seed is controlling the randomness. So the set seed makes sure that it does the same thing every time. It's still random. So when I run this, I get random numbers right here, but I can tell you the next time I run it, I'll get 4753 because I set my seed. So setting the seed, we get the same randomness each time. It's still random, but we get the same result. Without the set seed, we would not get the same result. We get different numbers every time, but 453, I think it was. There it is, 475. 475, and then the 3. 4753 is obtained because we have a seed set. It's kind of like Minecraft. Speaking of Minecraft, Smash Bros. Minecraft, everyone heard the big news this morning that Steve from Minecraft is going to be Smash Bros. He's going to, new character, new challenger. And so when you look at this right here, just think of Minecraft seeds, that if someone gives you a Minecraft seed, you'll get the same result every time. So that's what a seed does inside of R. You get the same result. So why are we putting a seed right here? Because this procedure involves some randomness. So it'll still be random, but it's just we could replicate it. It's like when you build a random Minecraft world and then it tells you the seed, the Minecraft world you built was random, but then you could replicate that world on another person's system. You could say, oh, you should play this world. And they'll be like, oh, what world? And you're like, that's a random world I created. It's random, but you can replicate it. So right here we have the y variable. This is the y variable we want to predict. We've learned a lot about this in 201 that we're asking a question, why is this happening? The dot right here means all the other variables. That's when I took my variables and put them into the x's. I dumped all the variables into the x's. This is the name of the data frame. Method equals random forest. So that's a random forest. Preproc equals center and scale. Everyone should know this. Center and scale means that we're turning them into z-scores. It means give them a center of 0 and scale them to standard deviations of 1. So that turns them into z-scores. The train control equals fit control is using this right here to control the internal validation. Tune grid equals forest grid. These are the CP levels. Is it CP? It is complexity parameter, but this goes back to Dan's question about when do we stop the tree? And so this is going to be right here. And then we're also going to stop it now via the cross-validation. Importance equals true will tell us the importance of the variables in the tree. So we can kind of do the same stuff. Let's go to data, survey 10. And let's see right here. I think survey 11 might have more interesting variables. Data survey 11. Let's look at survey 11 now. Survey 11, survey says, let's predict somebody being in Greek life. Oh, this might be the same data set, x08.Greek. This might be the same data set we have. So we need to go here and put x08.Greek and make sure we spell it correctly. Best way to make sure you spell it correctly by using this is to go to survey 11 $, and then do x08.greek, and then we spelled it correctly. The data is going to be survey 11, and everything looks to be good there. Now, let me make sure the CP, we should have some CP. There it is, expand grid, mtry. Oh, it's going to pick the CP for us. mtry is the number of variables it'll try in each tree. No, mtry. Why is my brain breaking on mtry? 2 seconds. Yeah, number of variables available for splitting at each tree node, for each tree node. Okay, let's... Oh, we're doing a random forest. The curve brought you back up to an A. That's awesome. That's so awesome. I'm so glad. I was like, what didn't make sense to me is we're doing a random forest. And I meant to just do a tree. So I wanted to do a tree. I didn't realize we were doing a forest. I was like, wait, why are we choosing variables? I was like, that doesn't make sense. That's only for a forest, but I did do the random forest, which the tuning parameters for that. So I'm going to go back up here and I'm going to do the tree. Tree's not as fun, but let's do it. So here we are. So let's do the tree. So you're going to see some, this is some 201 right here, Nick. So what we're going to do is we're going to use our part. Shouldn't there be a tree within? I guess there is. And then we'll use the CP. Okay, let's do this. So with this, let's go ahead and grab our variable names. And there's our Y variable. And survey 11. There's the CP, visualize tree. That's not going to be as interesting. And then, well, it's already here. Well, no. Fancy R plot tree. Okay. Oh my gosh. What did we do? Well, that's the tree there. Let me change the complexity parameter. There we go. Here's the tree right here. So this is predicting if somebody is in Greek life right now, and it's based on drinking. So it's Facebook friends and drinking, what we see. And let's change the complexity parameter again. There, oh my gosh, it's insanity. It is insanity. I'm actually more interested, oh, you can't read that. I'm more interested in the random forest. Still can't read it. Always hate. Let me try the other plot. When trees get too big, they're too hard to read. But you know, the insanity is really down here. We're just having some fun today. It's Thursdays. It's relaxing Thursdays. Let's go here and actually run the real deal on this. Let's run the forest. Missing values. Wait, I didn't run the grid. Missing values? What? Oh, is it some of the variables? I think some of the variables have problems. Error in NA default list. Greek. Shouldn't have a problem there. Oh, we can't center and stale Greek. Oh, and it's not categorical. So it cause a little more working with. I might just not do it with the tree because, yeah. Because we need to change the method, I think. I will not worry about that now. We'll focus on trees right now. We'll focus on trees. Nick, do you have any questions? What are you thinking about, Nick? Yesterday I was hitting all the answers. Today I need coffee, and I can't have coffee. No. Let's see right here. What questions are there? We've just mainly been talking about decision trees and partition models today. Boosted trees are a lot of fun. These are things we don't do in 201. So we could go here to a boosted tree, which is trees that learn from trees. You've got a lot of parameters here to control. So this is basically what you're doing with coding is you're controlling these parameters. Got the number of layers, split for trees, the learning rate, and let's go into our boosted tree. Ooh, that's not good. R squared of 0.3. Oh, we were doing video games. So I thought we were doing another one. That's way better than that one. Boosted trees totally destroyed it. So there's much better methods. How similar is the program to actually coding, or is this like coding? Like if I learned this program, would it be? Yeah, completely. So R is just programming or anything coding language. Yeah, R is a programming language. So you can, like here, I'll talk a little bit about programming to end. When it comes to R, you're just learning a programming language. So yep, I got a meeting right at 2, so I'll probably end like 5 minutes early. But this can just do mathematics, not just do, but you can do things like taking the mean. So everything we're doing right now in 201, you can do in here. And what's even easier is if we do a t-test, like let's say, so Nick, later on, you'll have to do a t-test with data that MyPearson gives you. So if MyPearson says like the weights of individuals are these numbers right here, like here's the weights of people. So MyPearson just gives you a data set of the weights of people. Does this make sense right here? So there's the weights of people. So it says, here's the weights of people, just gives you the weights of people. And then all you have to do is t-test, weight, and there's your t-test. That's it. There's a t-test. And then let's say MyPearson gives you data on the proportion of individuals. You could put in here prop test, and you could do the proportion. It even tells you. X is the number of successes. So let's say it says, how many mislabeled, or make a confidence interval for how many mislabeled packages of fish there are. So it says out of a sample of 120, there were 30 mislabeled packages. So what would we put in here? What would X be? It says out of a sample of 120, there were 30 mislabeled packages. So what would X be right here? And I'll talk a little bit more about the basics of what we're writing. So out of a sample of 120, there are 30 mislabeled packages. So X would be, what would X be? Out of a sample of 120, so think about what 120 would be in notation. Out of a sample of 120, and then X would be 30. There's the code. So N would be 120 because N is the sample size. So X is the amount of successes and N is the amount of trials. So out of a sample of 120, there are 30 mislabeled packages, and you can actually test a probability. You can say, it's prob, isn't it? Is it prob? No, yeah, I think so. We'll find out. Oh, that's a horrible, unused argument. The argument is, if you go here and write prop test, it'll show you it's P, because P is the true proportion. So we're going to guess that the true proportion is equal to 30%, and we can test there. You can also see if alternative, is it less than? Should be less. There we go. It even suggests things to you. So we can see if the true proportion is less than this amount. We get a confidence interval, and we also get a p-value for the test. And you see the p-value is not statistically significant. So you can actually run your test right here. And what's really fun is if you watch this here. So we could go right here and we could turn this into a function. So this is, man, I should write this for 474. I don't know if this would be too tough for them. But what if we turned this into a function that goes read line? So this is where you could help someone out. Do you know for any business analytics if I have to take any of your classes with this program? Oh, yeah, of course. Yeah, 320, 474, 471. Basically, I love it. I think it's great. I think it makes life easy. Regression, data mining, and Capstone all use it. And then Chung Lee uses it for time series. So it's excellent. How many samples did you take? So we're going to ask a person, how many samples did you take? And we're going to store this into N. And then, so they would do this right here, and they'd say 120. Then we ask a person, how many successes were there. Successes just means like observations that occurred that we're looking for. And then what value do you want to test? So we'll call this P. What value do you want to test? And it's, oh, yep, we ran it. And then, and then last but not least, what is your alternative? And I think if I go and go as dot character, we should be good on this. Okay. And then they have to enter less, so we need to put here. Can I do this? I'm gonna try something crazy. Enter less, greater. What were the other options? Two-sided. Enter two-sided, less, or greater. Let me see if that runs. Oh, am I still within my code? What is your alternative? Oh, it looks like that. Oh, that's horrible. We don't want to do that. So let's just do, even though this is going to look crazy. Oh, is it not there? There, oh gosh. Okay. And then we need one more. There we go. Okay, good. And then we'll go here and go less. Okay. So now we've basically coded a function. We've coded what we want to turn into a function. So we're going to go fun, and we'll go here prop walkthrough. And we're going to put right here choice. So we take all of this and we put it into here. And then we take this and we put our generic format. So let's see what we've created right here. We're going to put n x, so it's xn, right? X, n, and then p right there. So p equals p, or let's just put p in, or we'll do p naught. There we go, because that is p naught. And then we'll go choice right here. And let's try it. So prop walkthrough. Oh, and then return. Okay. So what we created is now it's going to walk someone through this. It says, how many samples did you take? And so we now say, I took 120 samples. How many successes were there? There were 30 successes. What value do you want to test? 0.30. What's your alternative? Enter sided, enter, oh, I might delete the two-sided. And I'm going to enter less. And it says, X, oh, I reversed them. How many successes? Oh, it should be N and then X. Is that right? I might have reversed it. Okay. How many samples did you take? 120. Did I enter the right? Yeah, there we go. 30. What value do you want to test this? X. Oh, it's not storing it as numeric. Oh, it's such a bummer. And then as dot numeric. And this is the fun of working with functions right here. I thought it sorted by numeric up in a number. Okay. Let's give it another shot. How many samples did you take? 120, 30, 0.30, less. X must be greater than, yeah, I thought this was in the right order. This should do it. How many samples did you take? What value are you testing? All that work for that. There we go. This is the fun of debugging functions. Something is wrong and you got to fix it. So I had to make sure they were numbers. If you notice what I did, I put it as numeric around it because when someone enters in these numbers, I want them to register as numbers. So when I entered in 120, I want to make sure it sees it as a number, not some sort of text. Because I think readline does text by default. It is like problem solving. Yep. And now this prop walkthrough, you could put this, there's ways to put these things on like websites with Shiny apps. So you can literally turn these into apps and things because you can, I think if we do this, plus new Shiny web app, let's go, is it not do a default one here? test app. You can make, yeah, it shows it right here. So check this out, save selected. This is a default Shiny web app right here, and you can change the bin widths of these histograms. So you could make your own applet, which I wish I was that quick on Shiny. I don't do a ton of Shiny. I mean, I've made my own Shiny stuff. I need to, if I did it more, if I did it for like a month and practiced it up and taught it to people, then I'd get really good at it. But you can make your own Shiny apps, and you could literally have fields where you could just enter it in, and then it would just display the results for you. I could probably code it up in 30 minutes. I don't have enough time now. I feel like whenever I'm using it, I'm doing it for fun. Yeah, exactly. Like, learn it, learn how it works, and the better you get with it, the more you understand it. If you learn things like Shiny, if you walk into a business and say like, hey, I can display your data and put it on websites and do these things. I mean, not like on the web so anyone can find it, but you know, R can do so many cool things, especially when you look at Shiny. So there's a lot of cool things going on right here. So this is just the bin widths of a histogram, and how when we change the bin widths, it changes the shape of the histogram or the way it looks. The shape is what the shape is, but the shape is dependent on how many bins there are, which is something we talked about early on. So it's just a bin width creator right here. So you would just create different fields and put in, yep. And so we would take, the goal now would be to take what we wrote here, turn it into a Shiny app. So that way you run the Shiny app, it would just report the results to you right here. You would just type the numbers in, and you could put this on the web for yourself. You could send it to someone and say, hey, I put a calculator on here to calculate the probabilities for you. Just put in the numbers. So you could do one for like each problem on the assignments. You could be like, how many fish were there that were this and this? And you could make an applet for each question. You just literally put the numbers in, and it would just solve it. But all you're doing is just writing the code to solve the question, and then just turning it into an applet to make it easier to use. That way it, you know. So when you think about it, it's kind of neat. I love the program. I love what we can do with it. And yeah, I think that's got it. I'm glad we got to talk about some like fun stuff today with Shiny. I've got a regression solver. Here, I'll show it. I'll show the one I built. Yeah, here it is. I showed this yesterday too. So I say, you know, I don't use it much, but then I built this. Oh, so here's the one I built. And let me load up the data real quick on here. I loaded the data yesterday. This will load, right? Okay, cool. So here is my app that I built. It took me days to build this. And you can go here to the data, and you can actually view the data. Is the data not loaded in? No, let me try this again. I only got seconds here. I'll go to ex2 census. Okay. So here we go. Here's the data loaded in, and you can choose a variable here like response rate, and you can investigate the variable. And yeah, I know. So you can look at all the correlations right here. You can look at the distributions of each of the variables. So you can pick a different variable here like urban. Yeah, it's insanity. And can I zoom out on this right now? There we go. So you can pick all the different things, like the different variables to look at. You can look at the scatter plot of it. And I even put in a smoothing line so you can see the relationship. So, and then you can get a model summary. So here's your output for the model. Check regression, did I get this working? I think I did, yeah. That was the hardest thing. This just did not want to work, the check regression. I'm trying to remember if it even works 100%. I finally was just like, okay, I can just do the check regression by hand. But I made this thing right here that does all the regression stuff for you and even looks for the strongest correlations. You can sort these tables. So you can click the variables, and then whatever you click here becomes the variable it looks at. So this is your outcome variable, your Y variable. So you can select a variable, and then you can search for correlations. So I made this tool right here as a regression model, and it's got the instructions right here. And yay, it was constructed by Brian Stevens with some help from Dr. Petrie's code. It basically uses tons of Dr. Petrie's code, but I'm trying to get better and better, and I just sometimes don't have time to build Shiny apps. But I wish every time I think about it, I'm like, oh, it'd be cool just to turn it into an app, and then you can just, it'll select the data. I have the same variable selected, so it's perfect correlation. Yeah, thanks. I appreciate it. This was a lot of fun to build, and it's kind of neat. Oh, it's even cooler with these graphics. You can like zoom in on them. So you can actually hover over the points, see the observation. You can remove things. So you could literally just look at the line. So there's the line. There's the smooth model through it. So you could look at kind of what linear relationships exist by removing the points. And it kind of gives you, that's interesting what parts of the line it zooms in on. I don't know what value. It's 0 to what now? Oh, it's changing the y-axis. That's weird. I don't like that it changes the y scale so much because the y scale, if you were to zoom in on this, you'd see that sort of thing. There's the zoom in pattern right there. Well, that's got it. I've got to head off to a meeting. Good job, everybody. A little bit of fun with Shiny at the end here, and I'll talk to everybody later. Bye, everybody. Thank you so much. Awesome job. Have fun in Montana. See you, Nick. Have fun.